Slide 1. Good afternoon. My name is Anderson Silva. I am responsible for the technical support and market development for the whole area of South America, and on behalf of BASF, I would like to welcome you. I have the pleasure to participate in this AmeriCaplast event, Food Packaging and Barrier Films, in which I am going to make the presentation Polyamides, Characteristics and Properties. This presentation is divided into two parts. In the first part I will be talking about the characteristics and properties of polyamides, and in the second part, I will be talking about the application of these characteristics and properties in some types of structures. Let's start. Slide 2. As well as other types of plastics, the polyamides have the repeating group in the polymer chain. We have ethylene, polyethylene, propylene, polypropylene, and polyamide, as its name indicates, in which the recurring groups are amides. Those groups are present in the chain, and they are responsible for the technical characteristics of polyamide, being also responsible for the mechanical strength, heat resistance, etc. Between these groups they have other groups that are hydrocarbon, carbon and hydrogen, which give some characteristics of flexibility and malleability, as well as transparency to the polyamide, and that also are present in the polymer chain of polyamide. Some types of polyamides are present in the natural environment such as meat, silk, wool. In Germany through the brand Perlin, which is known today as polyamide 6, or in United States as nylon brand, which ended up being the polymer's generic name, polyamide 6.6. Slide 3. Polyamides, like other plastics materials, are obtained through a chemical reaction between the monomers. These molecules are units that are repeated. The reaction to obtain polyamides is the polycondensation reaction, that is different to other polymers like polyethylene that are produced by an addition reaction in which these monomers come together, as if they were train coaches. In the case of the polycondensation reaction, there is a reaction between groups of the monomer forming a small water or even acid molecule. Polycondensation like this is among the two terminal reactive groups, one side acid and on the other side, the amine. The reaction between the acid and the amine will form amide, which is the product that we will be talking about in this presentation. And that reaction will be a balanced one between a molecule of acid and a molecule of amine. Slide 4. We have here two types of polyamides. A polyamide called type A, you have a reaction of an acid with an organic amine and that reaction forms an only monomer. This monomer will continue repeating someplace in the string determining the different features that are found in polyamides. In the second type called B, only one type of molecule of lactam reacts through a ring opening reaction, and from that opening, a complete molecule is obtained with the two reactive groups at the ends to react in the formation of the polymer chain. Slide 5. In plastic materials, the polymer's name is normally given by a repeated monomer, and this is the case of the polyamide 2. The ISO 1874 gives us an easy way to identify the polyamides through the atoms of the dicarboxylic acid. In the first case, the BASF product is a polyamide 6.6. The first 6 corresponds with 6 carbon atoms of the hexamethyldiamine, and the second 6 corresponds to the 6 carbon atoms of the adipic acid. Then we can notice that in accordance with the characteristic of that material is going to get a feature of crystallinity, subject that we are going to talk later. noticing as well that the composition directly affects the melting point. So, we see that in the polyamide 6.6 the melting point is in the strip of 260 degrees and polyamide 6 in the strip of 220 degrees Celsius. We can see other types of combinations, for example, in polyamide C that has two types of monomer, separated by a slash in the name. So, we see that we have a caprolactam monomer, which is the same than the polyamide ultramide C6 or ultramide B besides the polyamide 6.6 monomers, the hexamethyldiamine and the hexaneoic acid. According to the amount that is added the comonomer to form the copolymer, it is possible to obtain some differences in temperature or fusion, brightness, ease of processing, mechanical resistance. These are some features we are going to be evaluated in the course of this presentation. It is also used in nomenclature with letters in the middle of the numbers for those polyamides that have components that are not linear or aliphatic, such as, for example, the MXD6 in its monomeric composition. The letters are used to refer to the xylene diamine monomer used. This is a good demonstration of the types of polyamides that are used in the market in general. Slide 6. In this next slide we will identify graphically and quantitatively various types of polyamides that we saw in the previous table. For applications of barrier materials and multilayer for food packaging materials, which is the main subject of this conference, we notice that greater global participation of polyamide corresponds with 6 polyamide dominating applications, especially in United States and Europe, in contrast to South America, where applications of copolymers are still polyamides of copolymers, basically due to the difference of the production and manufacturing technology that generates these differences on different continents. Slide 7. We have just ended up seeing different types of polyamides and what the main types are. Polyamide 6 is a main type in the world, and also the copolymer 6.6 application packaging. Then, the use of the polyamide will depend on the requirement of the film in which will be applied, temperature, need of barrier or mechanical strength. In this specific slide that you are seeing now, check the wide range of products, for example of great use in United States, bags for roasted products with polyamide 6.6 for the requirement of high temperature, VARTM applications for wind turbines. Some are films with special polyamides, polyolefins, films normally based on polyamide 6. Also we can see applications where transparency is required in which we can observe the versatility of polyamides for the various applications with barrier chemistry requirements, mechanical resistance, transparency, thermal barrier, and also due to the versatility of the material that can be work processed with traditional equipment used for polyolefins without any super special equipment for their processing. Slide 8. The studies shows that the big problem that exists in relation to food preservation is an inappropriate packaging to accommodate the product. Why does it happen? Today we can notice that distance between food production places and centers of consumption of those products is increasing more and more. Therefore, with a suitable package we can extend the life of that product. We notice that one of the problems associated with inappropriate packaging is the high speed of quality loss in relation to oxygen and the oxidation, which can cause loss of quality by alteration of taste, changes in the types of fats and development of aerobic microorganisms. If some special technologies are applied to keep food conservation, The aerobics just grow more quickly. Besides, there is also a proliferation of insects. That is why the polyamide is used in packaging for storage of grains, since the smell of the beans is retained in the polyamide packaging, avoiding the attraction to insects. Therefore, we see that the advantages of the use of polyamides in the application has to do with the mechanical resistance and the barrier of conservation of those grains. These are very interesting applications for polyamides. 9. Something that we had not commented on the latest slides is that amide group is mostly responsible for properties such as resistance, heat resistance, resistance to the passage of oxygen. What is happening with these amide groups? These groups of hydrocarbons with amide groups end up forming unions of bridge type of hydrogen among them that improve the mechanical resistance of the polymer. Later, we'll see what the effect of the interaction of these links is with the humidity that is included among the links of polyamide's hydrogen bridge. Slide 10. In general, what we notice about the types of plastic packaging is that it is difficult to get the properties required in a monolayer packaging. So, to get all the properties and meet all the technical requirements of the packing, the use of a multi-film coating with multiple components is required. In the case of polyamide, we have a barrier to oxygen, to chemicals, resistance, stiffness, heat resistance, thermoformability, etc. In the case of polyolefins, barrier to moisture or water, sealability, flexibility. Thus, combining materials in different layers, it is possible to combine properties on demand by the final packaging, with various properties that are needed to be able to store this product. Slide 11. Then, as seen, the use of polyamides in the solution for packaging brings many advantages. It has just another puncture resistance, another mechanical performance or relationship strength, stiffness tenacity, a better transparency, which will also depend on the type of process and the transformation of this film. We are going to see in detail this topic a little later in the presentation in relation to more effective cooling to have a final material with an even greater transparency. We also have a good barrier to oxygen, where we have a good barrier to chemical substances and aromas, a good thermoformability of polyamide, high heat distortion temperature. And finally, according to the more demanding laws about the direct contact with food, in Europe, South America, etc. Slide 12. As well as also happens in other plastic materials, we also have a differentiation of properties related to molecular weight, having a direct influence on the mechanical properties. And in the case of polyamide, a very important influence on the variation of properties is observed for small variations of molecular weights. Here is the graph of the two curves of non-nucleated and nucleated materials that we are going to talk about later, that gives us the opportunity to observe the mechanical property variation, with the variations of the molecular weights in both cases. Slide 13. We previously talked a little about the crystallinity. What happens? The crystallinity is another way to identify these materials. The crystalline or amorphous materials end up with a difference in the mechanical behavior and strength, mainly the chemical resistance. For example, some amorphous such as polycarbonate, polymethyl methacrylate, polystyrene plastic materials. We also have some plastic materials that are semi-crystalline, polyamide 6, polyamide 6.6, PBT. and of course crystal structure materials. But today we are going to mainly talk about amorphous and semi-crystalline. So what is the difference between these two types of materials? Amorphous materials have a structure without form and disorganized, not having a clear melting temperature and defined by a lack of crystal structure that when the temperature increases it reaches the molten state or liquid. In semi-crystalline materials, part of the structures are organized and part disorganized, so, by increasing the temperature it shows clearly the vitreous Tg transition temperature that corresponds with the part of the crystal structure of the material, and then, it reaches the melting temperature of the crystalline part. The material is now fully melted and with the ability to closely match the shape of the transformation. A bar or a form, etc. Slide 14. And as I mentioned before when explaining the question of transparency, the properties of polyamides obtained by a certain process influence the degree of crystallinity. When the molecules in the polyamide are more together, a greater mechanical resistance is given as a result, but in return they will have lower optical properties due to the proximity of these molecules being more organized and tidy. For example, you have a polyamide 6 in a bubble extrusion process with an air cooling. We will notice that in some way the material is just becoming opaque because we need a while longer to let the crystals form. But on the other hand, if that same polyamide 6 is thermoforming through a process of cast or extruded flat with water cooling, the material becomes amorphous by cooling faster, not giving time to form the crystals. And that polyamide properties are affected by that percentage of crystallization as shown in the slide, plus by the morphology, distribution, size and type of used grade. Or if it's polyamide 6 or a copolymer 6.6/6. Also the additivation, as we saw earlier in the case of nucleated materials, because it just acts directly on the crystallization of the material and by the conditions of the process, as discussed above. Slide 15. As we have already said, polyamides are semi-crystalline materials and therefore, they suffer the influence of crystallinity on their properties. And again we see here, amorphous material, disordered structure, and on the side, a semi-crystalline structure, which allows us to play with the temperatures to move us in varying degrees of crystallinity and get different polyamide, for example, mechanical properties. Slide 16. Today we had specifically mentioned the conditions of cooling as a variable affecting the degree of crystallinity. Then when we have a slow cooling in an extrusion of film by annular head air cooled, we will notice this type of formation with a significant proportion of crystals. When we have a fast cooling, we notice that the structure remains practically amorphous and thus, the layer will present greater flexibility and superior optical properties. Then we have fast cooling, frozen and amorphous structure. Slow cooling with temperatures between 120 and 180 degrees Celsius. We have a growth of crystals directly affecting the properties of polyamide. Slide 17. We have then seen that polyamides are affected by this rigidity result of crystal growth rate, and here we saw everything that goes on with every type of structure in relation to the rigidity, the barrier, the transparency and the thermoformability. The first case of slow cooling to form crystals in greater proportion in an ordered structure. Rigidity is greater because more energy is required to separate these molecular structures. The barrier also is higher, because there is greater difficulty of the oxygen to cross the material. However, as we have seen, the crystal structure makes lose optical properties, and finally, more difficulty for thermoformability. In the other case of fast cooling, there's less initial crystallinity, then that the process ends to happen a certain degree of reorganization that gives the material some organization called post-crystallization, with structures somewhat more elongated. The stiffness is lower. The barrier is comparatively minor, but with better optics and thermoformability properties. One interesting thing is that the barrier is lower if we evaluate a film in terms of its flat state prior to thermoforming. The barrier is very influenced by the ease of stretch of the material into the mold, and as it has a less rigid structure, in the case of rapid cooling, the structure ends up being a bit more rigid with higher barrier structure mainly on ridges or edges. That is the critical point of the structure thermoformed, as a result of thermoforming or deformation energy work, to finally have a packaging with a better barrier in that part of the thermoforming, despite the fact that the amorphous structure of the flat film is comparatively less than the slow cooling.